Welcome to Statistics, Random Data and Sampling on DataFrames. After completing this lesson, you should be able to compute column summary statistics, pairwise statistics between series and columns, perform standard and stratified sampling on any data frame, and split any data frame randomly into subsets and generate random data from uniform and normal distributions. In the previous module, I've introduced column summary statistics for RDDs of vectors. Now I introduce column summary statistics for data frames. There are two ways to proceed. The first and most straightforward one is the describe method, which returns another data frame with 5 rows containing column-wise results for min, max, mean, standard deviation, and count. However, we recommend the second method as some users experience issues in using the summary statistics table outputs for further calculations. The second way is to use both group by and aggregate methods, which also returns a data frame with the results, but only one statistic can be returned for each column. So it's possible to get minimums for all columns or a different statistic for each column, but not all statistics for all columns at once. Notice here that the standard deviation is not supported by these methods. This is a simple example of summary statistics using the describe method. First, I import implicits from the SQL context, so I can turn an RDD into a data frame. Next, I define a case class named record, which encapsulates a description and 2 values. Then I create a data frame containing 3 records named recdf. And now I can compute column summary statistics by calling the describe method on my data frame. I assign the result to another data frame named recstats and show its results. And as expected, the return data frame is 5 lines long and contains statistics for all numeric columns, that is, value 1 and value 2. So computing column summary statistics is quite easy. Now I'm going to work a little bit on fetching or extracting the results from the data frame. If I'm interested in a particular statistic, say the standard deviation, I can filter the data frame using summary equals stddef, and then fetch the corresponding results with first, since I'm guaranteed to have exactly only 1 line left. It will return me with an instance of row as shown in res0. But perhaps that is not the most convenient way to handle the results. So I may cast it to seq and to array, so I end up with an array of any as shown in res1. Notice the description of the statistic itself is on the array. So next I drop it and map everything else, that is the actual results, to double. Now I have standard deviations for all numeric columns as a double array, as shown in res2. Please note that some users experienced issues in using extractions from the summary statistics table within certain implementations of Spark. So you may wish to try the following alternatives in this slide and in the next if things aren't working out for you. Supposedly, I may be interested in all statistics for a given column. So I may select that particular column, for instance, value 1, and map all elements to string, and then to double. The result is another double array, as shown in res3, with column statistics in the following order: count, mean, standard deviation, min, and max. Here we have another simple example of summary statistics, this time using both group by and aggregate methods. I use the same data frame named recdf and call the group by method with no arguments, thus using the whole data frame, and then call the aggregate method with a map, where keys are column names of the data frame and values are the corresponding statistics I want to compute over that particular column. In my first attempt, I have a map containing twice the key value of 1 with 2 different values, as if I wanted to compute both minimum and maximum for the column value 1. But it does not work that way, and I end up with only the maximum for this column. Remember, only one statistic can be returned by column using the aggregate method. Then in my second attempt, I can compute the minimums for columns value 1 and value 2. And indeed, the resulting data frame has results for both. If you first import org.apache.spark.sql.functions, here is an alternative way you can derive the same results without writing the map function. I can fetch the description of the return statistics using the columns attribute of the resulting data frame as shown in res 0, and I can fetch the statistics using the same approach shown in the previous slide as shown in res 1. Now I introduce yet another set of statistics available on DataFrames. The stats method returns a DataFrames stats function object which has another set of methods for computing Pearson correlation and sample covariance between two columns, as well as pairwise frequency table for a given set of columns. Also, there is a method for finding the most frequent items in a column, although it may yield false positives. This is a simple example of these set statistics. Again, I'm using the same data frame named recdf and call the stat method in order to get an instance of DataFrame stats functions. Then I compute the Pearson correlation between columns value 1 and value 2, which is approximately negative 0.59 as shown in res 0. And the sample covariance between the same columns is about negative 3.57 as shown in res 1. Then I call the frequent items method, passing as arguments the column over which I want to perform the operation, that is, value 1, and the minimum proportion of rows, in this case 0.3 or 30%. This is a one-pass and approximate algorithm which may yield false positives. So in this toy example, it returned all 3 rows even though I asked for just 30%. Of course, this kind of operation is supposed to be performed over much larger data frames, and this result is just to illustrate the method's inputs and outputs. Now let's turn to sampling on data frames. Sampling can be performed on any data frame and returns a sampled subset of it. It can be done with or without replacement, and in either case, the fraction passed as argument is the expected, not the exact fraction of rows to be generated in the resulting data frame. As one could expect, sampling on data frames is very useful for bootstrapping procedures. This is a simple example of sampling a data frame. I create a data frame with 7 key value pairs and name it DF. Then I just sample 30% of its elements without replacement, using 11 as a seed and assigning it to another data frame named DF sampled. This operation results in 2 elements sampled, which is roughly 30% of all 7 elements. In the previous lesson, I've introduced the random split method on RDDs of vectors, a hassle-free way to split a dataset into multiple subsets without having to be concerned about the approximate nature of standard sampling. The same method is applicable to data frames, returning an array of data frames of sizes proportional to the array of weights passed as an argument. Again, if the weights do not add up to 1, they are normalized prior to the splitting. Now we look at an example of a random split. This time I use the same data frame with 7 key value pairs and call the random split method specifying an array of weights. Now I want to split the data frame into 2 parts of sizes 30% and 70% respectively. And I use 11 as a seed. It returns me an array of data frames named DF split. Its second element is a data frame which contains 4 of 7 elements of the original array, roughly 70% as specified in the arguments. The third type of sampling is again the stratified sampling. It can be performed on any data frame and any column may work as a key label. For each key, it may be specified a corresponding expected fraction of elements to be drawn that are associated with that particular key. Stratified sampling can only be performed without replacement. It is available as sample by function in the DataFrames stat functions object. This is an example of stratified sampling. Again, I use the same data frame with 7 key value pairs. Notice that I call the stat method of the data frame in order to gain access to the DataFrames stats functions object, which implements the stratified sampling procedure. My key is the column named key, and for each possible value, 1, 2, or 3, I specify a fraction, in this case 70%. So I want to draw approximately 70% of the elements in my data frame while keeping the original proportion of the keys. In the original data frame, I had twice the keys equals 1, 3 times the keys equals 2, and twice the key equals 3. The resulting stratified sampling returned me 2 different elements for each key, thus preserving the original proportion as much as it can, given the approximate nature of the algorithm and the quite small size of the example. Moving on to random data generation. Here we use SQL functions to generate columns filled with random values. There are 2 supported distributions, uniform and normal, and we mainly want to generate random data for use in algorithms, prototyping, or to test the performance of our model. This is a simple example of random data generation. I start by importing the corresponding SQL functions for uniform and normal distributions, that is, rand and randn. Then I create a data frame from a range and name it df. Next, I append 2 columns to its original ID column, naming them uniform and normal, and using the functions rand and randn with seeds equal 10 to generate the corresponding random values. It returns me another data frame with 3 columns. The first 5 rows show some of the values generated randomly. Having completed this lesson, you should be able to compute column summary statistics, pairwise statistics between series and columns, perform standard and stratified sampling on any data frame, split any data frame randomly into subsets, and generate random data from uniform and normal distributions.